think I accidentally ended the meeting. So welcome to the webinar. And okay, while people are gathering, while people are coming back to the webinar, can I just have a quick feedback? Which should be okay. Is the audio fine, guys? Is the audio fine? Can you hear me well? What about everyone else? Okay.
How about now? Is it better now? Okay. Right. Okay, that's fine. So I'd like to ask you which problems in physics. So I had a poll this morning. So which was the most challenging, and most of you said physics was more challenging. So could you tell me which questions in particular? You maybe just indicate 2 or 3 which you found particularly difficult, and I'll have a look. COMPOS, Oxford. So we can 12, 10, 4. Let's have a look. Let me open the 12, 10, and 4. 4. Oh, yes, 4. 4 is an exciting one. 9. 9 is the same as problem 3. Okay. For 10. Okay, and 12. Well, 12, yes, a difficult one. Anything else? Anything else? Okay. Well, for problem 10, I have a very similar problem right here. So we will do that. So just give me a moment. I'll just quickly add this problem to the list of problems, and that's problem 5. Problem 5. So what we have is alpha is 30, and mass is 50 kilograms, and F is 294. Find R and find acceleration. Okay, anything else? So problem, not yet. Problem, you said problem 3, sorry, problem 4. Okay. I'll put that down and I'll see what I can do. Okay, problem for this is the problem from the assignment, and let's indicate problem 5. Oh no, problem 6. Okay, right, I'll share my screen. I'll share my screen. I'll leave the chat on. Okay. If you can see my screen, please type 1. Also, I can't see how many people are here today. Okay, you can see my screen. Oh, okay. Just 15 of you. Right. Okay, not too bad. Okay, so first I wanted to finish problem number 5, which we didn't finish last week. So the question is, M1 is frictionless and M2 has a friction coefficient of 0.3. Find the acceleration of each mass and the tension in each string. Okay, so as I've mentioned last week, the key thing here is to accurately draw the forces acting on each block. So I'm going to start with block M3. That's the easiest one, and it has 2 forces, M3G, 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 and the tension. There are 2 ropes, so we'll need tension 1 for this rope. Now that's fine, and we can write down Newton's second law. So we assume that it accelerating down. It's not always the case. It's our guess that acceleration is down, and we write down that M3A is equal to the forces acting along the acceleration, M3G, minus the forces acting against acceleration, minus T1. So this is Newton's second law for this block. Then we have block M2. So M2. So let's draw the forces acting on M2. So for M2, there is tension 1 acting this way. There is gravity, weight, acting downwards. There's tension T2 acting this way. And also we have friction force. So we can indicate it like this, the friction force acting this way, assuming that the block goes up the slope, which is very likely because M3 is 4 kilograms, so M3 is heavier. And finally, we have the normal reaction force, R2. Okay, so let's label them R2. There is the tension 1. There is tension 2. There is M2G. And this force, well, if it's moving, we can safely assume that this force is equal to mu R2. Mu R2. And we write down, and remember the trick that we did, we put the x-axis along the slope. We put the x-axis along the slope, and we put the y-axis perpendicular to the slope. So we do Newton's law in the x direction and in the y direction. So in the x direction, or along the slope, in A-level books, it says along the slope, which is just a different way of saying along the x-axis. So along the x-axis, yes, along the x-axis is going to be T1. Sorry, I've got M2A. And acceleration is the same because they are connected to an inextensible rope. Therefore, the acceleration for the first and the second and the third block will be the same. And M2A, so we need to split that, the mg force, into components. We need to split that into components, and this would be this, because this is theta. This is M2g cos theta, and this is M2g sine theta. And here we go. So M2A is going to be equal to T1 minus T2 minus mu R2 and minus M2g sine theta. So all the forces acting along the acceleration, because the block is accelerating this way, acceleration is this way, in the x direction, M2A, and in the y direction, we have just two forces, R2 and M2g cos theta. And the acceleration in the y direction is 0. So we can say that these two forces are equal. So we can say that R2 is equal to M2g cos theta. Okay. We have this. We have these two equations. And finally, we have the third block, which is M1, And the forces acting on it is mg. I'll use black. Mg, M1g. Then there is the tension, T2. Then there's the normal reaction force. And there's no friction. So this block does not experience friction. So that makes our life a little bit easier. So T2, then R1 and M1g. And we can split mg into two components. This is mg, M1g sine theta. This is M1g cos theta. And let's write down Newton's second law. So in the x direction, it's going to be M1a, acceleration is the same, is T2 minus M1g sine theta. And that's it. I mean, in the x direction, there are no more forces. And in the y direction, we have R1 is equal to M1g cos 30. They are the same because these forces, these two forces must be the same because it's not moving in the y direction. Okay, and as I said, this is where physics ends. This is where math starts, because all you need to do now is solve these simultaneous equations. And it might look daunting at start, but once you start looking into it, it's not that bad actually. So what we'll do is we'll choose the bigger equation. This is the bigger equation, and just put everything into that. So we substitute all the unknown values into that. And you might notice that R1 is nowhere to be found in here, so you won't actually need this one. You don't need this one because it doesn't give you any information. It just tells you that it's not moving in the y direction. So that's what we'll do. So from here, from the first equation, we get T1 is equal to M3G minus M3A. From the second equation, we just substitute it here. We substitute R2. That makes sense. So from the second equation, let's call this the second equation, we get T2, which we will need. T2 is M1G sine theta plus M1A. Okay, yeah, that makes sense. And we plug that into here. We put that into here. So we get a long equation, M2A equals T1. T1 is M3G minus M3A minus T2. T2 so it's minus M1G sine theta minus M1A. So that's T2 minus mu times R2. R2 is M2G cos theta. So M2G cos theta. And finally, minus M2G sine theta. Lovely. And now we've got just one equation to work with, with only one unknown, and the unknown is A, and that's what we will be looking for. So A, so I take everything with A to the left-hand side, so it's M2 plus M1, 1 plus M3 equals, and everything without so M3, you know what, I'm just going to cheat a little. I'm just going to copy that and delete the A's. Okay, and then finally I got acceleration is equal to this thing, this thing over this thing. Wow. Just for the sake of it, I'll switch those around. And this is the answer. This is acceleration. So when you're doing physics at a high level, this is the kind of answer you give. This would be the answer. But then they say, oh, we were very kind and given you M1, M2, M3 and friction. So let's plug that in and get a numerical value. So acceleration is, right, M3 is 4, I believe. M3 is 4, 1, and 3. Okay, I'm not going to remember that. Okay. So all you need to do is now plug that in. So it's 4g minus m1g, so 3g sine theta, and theta is 30 degrees. Yes, theta is 30 degrees, so sine 30 degrees is a half. So 3 times a half, so it's going to be 1.5 g minus 0.3 multiplied by m2 multiplied by 1 and multiplied by g and multiplied by cosine. So cosine is square root of 3 over 2. Square root of 3 over 2 and g. And minus m2, which is 1 kilogram again, times sine, so 0.5 g over 3 plus 1 plus 4. So you get 4. Okay, I'm just going to use my calculator for this. Minus 1.5 minus 0.3 square root of 3 over 2 minus 0.5 minus 0.5 divided by 8. So 0.2175 G, which is, oh, you have to put approximately here, approximately, which is approximately times 9.81, 2.13 meters per second squared. Okay. How much sense does this make on a scale of 1 to 10? Okay, lots of 9s and 10s. Lots of 9s and 10s. Good. 9. All right. So it's just a matter of doing the diagram, writing down using second law accurately. That's all it takes to do this question. And the same for all other questions. Same for all other questions. So let's do this one. This one is not that hard. So remember when I started doing this last week, and somebody pointed out that this system is going to move the other way around from what I said initially. But let me demonstrate to you that this is not a problem. So I see that M1 is 100 grams and M2 is 300 grams. So probably this mass will move down and this mass will move up. But let's say I've missed that fact. I haven't realized this fact. And this is exactly what happened last week. I didn't realize that this mass was more than 2 times bigger, because that's the criteria. It has to be more than twice the first one. So I still write that my acceleration here is downwards and acceleration here is upwards, but because of the way the ropes are arranged, this mass will move twice as slow as this one. So to understand this better, what I'll do is I will draw a horizontal line here. Okay, and let's give it a name. So let's say it's A, B, C. And let's say I'm pulling on the rope. When I'm pulling on the rope at this point will move upwards. This point will move upwards. But as you can see, C, nobody's pulling C. So C is stationary. C is stationary. So, and this is exactly what happens. I'm looking at the line ABC. A, B, and C. And suppose that A has moved a distance x upwards. A has moved upwards by a distance of x. But because C did not move, that means B has moved upwards by a distance of x divided by 2. Just a quick vote again in the chat. Do you understand why B moves half the distance of A on 1 to 10? Okay, and that tells me that the acceleration of the second block, which is tied to the center of the moving pulley, the acceleration of this block is going to be half the acceleration of this block. So this is A, and this is A over 2. And this is a very important thing to understand. And then all we need is just writing down the equations. So, and let's have a look. So for the first block, so I'm just going to scrap what I've written. Just ignore that. Although it is correct. I mean, I'm just going to do it again. So I draw the first block. One of the very important things to do is draw just one block. And there is the M1G. M1G acting downwards and T acting upwards. And let's write down the Newton's second law. So we assume that it's moving downwards. So M1A is equal to M1G minus T. And then for M2, well, M2 is connected to the pulley. The pulley is very light, but there's clearly two T forces here. So there's a T force and another T force. They are here. And one force acting downwards, M2G. And we write down M2A over 2, acceleration of this one, is equal to T plus T minus M2G. T plus T minus M2G. Okay. And all we need now is to solve. So from the first equation, I get T is equal to M1G minus M1A. I rearrange that. This is my first equation. And I plug this into here. So I get M2A over 2 equals 2T. So 2T, which is 2M1G minus 2M1A minus M2G. And well, what can I do? I'm going to multiply it by 2 and take this term to the left. So it's going to be M2A plus 4M1A equals 4M1G plus minus 2 m2g, and I get acceleration is equal to 4 m1 minus 2 m2. I'm taking g out, so g is here, divided by m2 plus 4 m1. And now I can, as a matter of fact, I don't even have to convert. I don't have to convert this to kilograms, because whatever units I use for this fraction, the units will cancel out, because this is grams and this is grams. So I can safely use 4 times 100, so it's 400, minus 2 times 300, so it's 600, divided by m2 plus 4m1, so it's 300 plus 400 g. So I get minus 200 over 700. So I get minus 2 over 7 g. And surprise, surprise, my answer is negative. That means that my initial idea that it will be accelerating downwards was wrong. Therefore, because A is negative, that means block M1 is moving upwards and block M2 is moving downwards. So you see, not guessing if you don't know the direction in which the block will move, you guess. If your guess is correct, you get a positive answer. If your guess is wrong, you get a negative answer. Now, it gets slightly harder with friction, because friction changes direction depending on which way it is moving. Okay, but yeah. Okay, right. Moving on. Okay. Just a second. Right. Any questions? Oh, the rope has a fixed. Yeah, the rope is inextensible. Yes, you can't extend the rope. Like in all physics questions, if it doesn't say otherwise, yeah, it is fixed length. Just a second. Right. Okay, so any more questions? Okay. Right. The hula hoop question. I think it's spelled like this, hula hoop. Spun quickly and thrown along the floor. I'm getting even closer to the original problem. So how far will it travel before reversing its direction? So let's talk about that. So you've probably seen the video, quite a fun thing to do. If you have a hula hoop at home, do experiment. And so what's going on is that we spin it very quickly. We spin it quickly means that it is sliding and not rolling. And if it's sliding, there's only one force, the one horizontal force acting on it, which is the friction force. So let's draw the forces acting on the hula hoop. So the hula hoop is traveling to the right with initial speed 10 meters per second. And it is spinning it is spinning that way with some angular velocity, which we don't know. We're not really interested in what the angular velocity is. But the thing is, it's slipping. And in this slipping gives rise to a friction force, which has a direction to the left. And the size of that friction force is mu r. Because it is slipping, we know exactly the size of that force. And of course, there's the normal reaction force. There's the normal reaction force here. Normal reaction force, and there's the weight force, which is mg. So we can safely say that the reaction force is equal to mg because it's not going upwards or downwards. That's easy. And then we can write the Newton's second law for the horizontal movement. So ma, mass acceleration, is equal to minus mu r. So we just take the x-axis to be in this direction. So mass acceleration is minus mu r. And that's almost it. I mean, we've almost got the answer now. So what happens is, as the hula hoop is traveling, it will decelerate, it will slow down. And you've seen that in the video, it will slow down. And then if it has enough backspin, it will start rolling backwards, or start accelerating backwards. So let's write this down. So from here, we substitute r. So we have ma equals to minus mu mg. And mu cancels out. So acceleration is minus mu g. And for simplicity, assume g is 10 meters per second squared. So we get minus 0.5 times 10. So minus 5 meters per second squared. So now we know the acceleration of the hula hoop. And the question is, how far did it travel before reversing its direction? So when it's reversing its direction, if we write down a Suvat equation, what does it mean that it changes direction? Can somebody help me with this one? Yeah, final velocity is 0, exactly. So we'll take the equation which doesn't contain time. So displacement is equal to u plus v divided by, I said the one that doesn't contain time, and I'm using the one that does contain time. Sorry. So 2as is equal to v squared minus u squared, this one. And the displacement is equal to v squared minus u squared over 2a. So that's final velocity, which is 0 squared, minus the initial velocity 10 squared, and divided by 2a, which is 2 times 5. 2 times 5, and that's minus 100 divided by 10, so it's, oh, acceleration is minus 5, of course. Acceleration is minus 5, and then it makes sense. So it's minus 100 divided by minus 10, which is 10 meters. So the hula hoop will travel 10 meters along the floor and then start accelerating backwards. Now in your problem, it says that it's rolling backwards. That means it accelerates for some time and then stops accelerating. That is simply enough another Suvat. All right, and we can find the time as well. The time to stop time to stop is the initial velocity divided by well, final velocity minus initial velocity divided by acceleration. So that's final velocity is 0 minus 10 divided by minus 5. So it was 2 seconds. It will stop in 2 seconds and start accelerating backwards. And in the problem number 12, the acceleration, the backwards acceleration would be the same, obviously, because it's still slipping, but at some point it will start rolling. Once it starts rolling, it has no more acceleration. It's not accelerating anymore, and it's traveling at constant velocity. This is what you need to realize to solve that problem. I think I might have said too much. All right. Anyways, okay, so here we are. This is a slightly easier problem. So you have 3 masses on a smooth table. 3 masses on a smooth table, and there are 2 forces acting. 1 force to the left and 1 force to the right. And it's given that the force to the right is bigger than the force to the left. And if this is a smooth table, that simply means that they will all accelerate to the right. The acceleration of each mass would be a. Okay, and then we can simply start writing down Newton's so write down M1, M2, M2, and M3, and just indicate the forces acting. Now, in dynamics problems, I mean, for every mass, the vertical forces would be balanced because the blocks are not moving upwards and not moving downwards. So the vertical forces are of no interest to us. I mean, we could write down that for every block, the reaction force is equal to mg, but that doesn't give us anything. That just makes things more complicated. So we can ignore the vertical forces and focus only on the horizontal ones. So for block M1, there are 2 forces, F1, and the tension. Let's call it T1. T1 would be slightly bigger than F1 because it's accelerating to the right. And we write down Newton's second law, M1A is equal to T1 minus F1. For the second block, there are 2 forces. There's T2 and T1. And once again, T2 is slightly bigger than T1. So M2A is equal to T2 minus T1. And finally, M3, very similar picture, F2 and T2. So M3, A, mass times acceleration, is F2 minus T2. Okay. And so from the first one, we get T1 is equal to M1A minus F1. From the third one, we get T2 is equal to F2 minus M3A. And we put that into here. We put that into this middle equation. So M2A equals T2, which is F2 minus m3a minus T1, which is m1a plus f1. Yeah, I'm changing the signs here. And take everything to the left. So acceleration multiplied by m1 plus m2 plus m3 is equal to, oh, that doesn't make any sense. Where did I go wrong? Yes, thank you. Exactly. And so this is going to be minus. Thank you. Yes, this is plus. I'm just failed to rearrange it correctly. So a T1 is M1A plus F1. And then it's equal to F2 minus F1. So acceleration is F2 minus F1 divided by the total mass, M1 plus M2 plus M3. This is the answer. This is the answer because F1 and F2 is something that is given to us. So we assume we know it. And M1, M2, M3 are also given to us. So this is the answer for A, for the acceleration. But we need the tension in the left rope. Sorry, it's not the answer, but that's the value for A. And then we need the tension in the left rope. So T1 is equal to M1A plus F1. So it's going to be M1A. So M1 multiplied by A, which is F2 minus F1, divided by M1 plus M2 plus M3, plus F1. This is the value of T1, also expressed in known. So if I give you the numbers for F1, F2, M1, M2, M3, you can simply get the numerical answer. But you're not interested in numerical answer, the numerical answer here. We're interested in, well, kind of doing physics here. So how does A make sense? Well, I'll talk about A in a minute. We can also do T2 in a very similar way. So T2 is equal to F2 minus that. So it's going to be F2 minus M3 multiplied by A, F2 minus F1 divided by M1 plus M2 plus M3. So you get an expression for T2 as well, because why not? This answer, let's talk about this for a minute. We can, if we just needed to find A, we could simplify this problem dramatically and say, what if all these blocks are just one block of mass M1 plus M2 plus M3? M1 plus M2 plus M3. And there are two forces acting, so F2 and F1. F1. So all I need to do is write down Newton's second law. Newton's second law, it says mass acceleration is equal to the sum of the forces. So M1 plus M2 plus M3, this is the mass, times acceleration is equal to the sum of forces. And in this case, because it's accelerating to the right, we can say that the x-axis is in the right direction. So we have F2 minus F1. And we get the same answer by treating 3 blocks as one. And this is sometimes incredibly useful. F2 minus F1 and simplifies this solution to problems M3. Okay. Right. Any questions? Okay. So problem 5 is very similar to problem 10. Problem 10. You have a horizontal force and the block is at rest. In this case, it's not at rest, it will be accelerating. But the equations are the same, it's just different variables. So what do we know? Sorry, let me just peek. Oh, it is a smooth. Okay, let's make it unsmooth. So let's modify this problem and say that mu is equal to 0.2. 0.2. So find the reaction force and find the acceleration of the block. Okay, so what can we do here? Well, we can draw the forces. Draw the forces on the block. This is I always say draw the block separately, but in this case, it's honestly not necessary because you don't need the Newton's second law for the slope. So that makes life easy. So I'm gonna draw the forces acting on the block. So there is mg. There is the normal reaction force. Normal reaction force. There is the friction. There is the friction. Now, let's leave it just as friction. So this is normal reaction force. This is force of friction. And we know that force of friction is less than or equal to mu r. Okay, then we have the force of friction. Oh, that's it. Then I split mg into components. And this is going to be mg cos alpha. And this is mg sine alpha. Sine alpha. If you're not confident with these things, do practice. Do practice a lot because this will help you. This will help you, honestly. You need to be very confident with splitting vectors into components and drawing diagrams for inclined planes. Now I'm going to split the F force as well because the F force is not along the slope and not perpendicular to the slope, so I need to split it into components as well. So I'm going to split it into a component like this and a component like this. So this is F cos alpha and F sine alpha. And then for convenience, I take the x-axis along the slope, and I take the y-axis perpendicular to the slope. So I say this is the x-axis, this is the y-axis, and I write Newton's law in the x direction and in the y direction separately. So in the x direction is going to be ma is equal to the positive, because x-axis is down the slope. So the mg sine alpha is positive. Sine alpha is positive, plus f cos alpha. Cos alpha is positive. And negative, we have minus f friction. F friction. And y is the positive is r plus f sine alpha, minus the negative is mg cos alpha, and it's equal to 0 because it's not accelerating. It's not accelerating perpendicular to the slope. We assume that it is in contact with the slope, because that's what it says. It's in contact with the slope. 294 newtons, and 50 kilograms degrees. Okay. Now, the difficulty arises here. We kind of need to evaluate. We need to understand whether it's stationary or moving. So one thing is that we can guess, because why not? We can guess, or we can do a quick evaluation. Okay, so mg, well, okay, we can assume that it is moving, and if we get a negative answer for A, that means our assumption was wrong. Assume the block is moving down the slope. If this leads to a negative 0, then our assumption was incorrect. This is what I keep in mind when I start. And by doing this, it makes life easier, because if I assume it is moving, that means that F friction is exactly mu R. And I write down the equations. Ma is equal to mg sine alpha plus F cos alpha minus mu R. So in the problem number 10, you would need to assume that A is 0. It's moving with no acceleration, so A is 0. For problem number 10, acceleration is 0. This is just a hint for you. F cos minus mu R. So mu and R from here is mg cos alpha minus f sine alpha. You can write it here. So R is mg cos alpha minus f sine alpha. Okay, minus mu mg cos alpha plus mu f sine alpha. So we're expanding the brackets here. And I think that's it, pretty much. Acceleration is equal to this thing, this monster, mg sine alpha minus f cos alpha minus mu mg cos alpha minus mu f sine alpha, and divided by m. So I plug this in a calculator. So m is 50. 50 times, okay, since I'm using a calculator, I'm going to use 9.8. 1 times sine alpha is half, 0.5, and minus f, which is 294. 294 times cos alpha, which is square root of 3/2. Don't remember the numerical value. Minus mu 0.2 times m, which is 50, times g times 10 times cos alpha again, so square root of 3/2, minus mu, which is 0.2, f, which is 294, and sine alpha, which is 0.5. And this all over 50. 50 and fraction. Oh, sorry. I said that g is 9.81. I'm contradicting myself. 9.81. So 50 times 9.81 times 0.5 minus 294 times cos 30. I'm in degrees, yeah. And minus 0.2 times 50 times 9.81 times cos 30, minus 0.2 times 294 times 0.5 all over 50. You get acceleration. Which is negative. I get acceleration, which is negative 2.47 meters per second squared. So that means my assumption was incorrect. This led to this. So my assumption was incorrect. Therefore, I don't know the friction force. But that tells me that my assumption was incorrect, that in fact, the block is stationary because the force is not equal to that. Assuming I haven't messed up, and I think I might have, I can see one mistake here, plus, so let's try that again. Don't worry, I'm going. Zero 0.2 times 294, so that's going to be a plus. Minus 1.2, so still negative. Still negative. Minus 1.29. 29. So my 1.30. 1.30. So f cos Sorry, guys. I don't know what happened today. So plus. Okay, now it makes sense. Now it makes sense, and it's going to be 8.88, 8.9, 8.9 meters per second. Just a second, guys. Yeah, sorry. Yes, so it's 8.9, so it's accelerating down quite rapidly, and yes, yeah. I wonder how I managed to make so many mistakes in one question. But anyways, 8.9, and so our assumption was correct. And now they also ask us to find R, and R is, we have R is equal to mg cos alpha minus f sine alpha. So that's going to be m, which is 50, times 9.81, times cosine, which is, well, cosine 30. Your calculator can deal with that. Minus f is 294, times 0.5, which is sine 30. So that is 50 times 9.81 times cos 30, minus 294 times 0.5 is 277. So this is the contact force between the block and the, so 278 newtons, three significant figures. Okay, so that's that's for problem 10. Finally, we approach this problem. What, well, the force needs to apply to the trolley. The blocks are stationary in the frame of reference of the trolley. Friction is negligible. Well, how do I do this question without doing this question? And let's modify this question. Let's modify this question and say, so there's a trolley. There is a block on top with mass m. The bottom block is mass m capital. Now, there's a spring here which is attached to a spring, and the spring constant is K. The question is, what is the force that needs to be applied to this? What is the force that needs to be applied to the trolley? What is the force? The force that needs to be applied to the trolley so that the spring extends by well, let's say x meters by x. Well, okay, by x. Okay, I might have made this more complicated in a way. The spring extends by x. Yeah, okay, we can keep it like this. So just a reminder, because we haven't done the Hooke's law with you. So if you take a spring and apply a force F to it, let's take a horizontal spring. If you take a spring of spring constant K, and you apply a force, the spring will extend, so the spring will become longer. So the spring is like this. If you apply a force F to it, the force will extend by x, and F equals kx. Or in other words, x is equal to, well, the modulus of F divided by k. Let's be strict here, because technically force is minus kx. So the spring will extend by this distance, if that makes sense. The force will extend by this distance, just from the Hooke's law. The Hooke's law is F equals minus kx. Minus because the force is backwards. Well, we can avoid dealing with in signs by just introducing the modulus here. So okay, so extends by x. So we draw the top block, and there we assume that the surface is smooth, so there's no friction. So the only force acting, in fact, is the force from the spring. And the force from the spring, the tension in the spring, is kx. Kx is the tension in the spring. And now we draw the trolley. We draw the trolley, and it has a force F. And in fact, so there is the nail here. So according to Newton's third law, it experiences an opposite force, kx, backwards. So the key thing here that you need to understand is that both the trolley and the block are accelerating to the right with acceleration a. And this is true here. This block is accelerating this is accelerating, and this is accelerating. However, this block is not accelerating upwards, up or down. It's only accelerating to the right. So you just need to carefully draw the forces acting on the three blocks and write down Newton's second law. So this is acceleration. This is the acceleration. So mass times acceleration is equal to kx. That's the only horizontal force. Yeah, we ignore the vertical forces here because they're of no interest to us. So m equals kx, and in this case, m, a, mass acceleration, is equal to f minus kx. Okay, and oh, isn't that it? Isn't that, oh, we need the acceleration. Okay, so from the first block, we get acceleration is equal to kx over m. And we plug it into here. M equals m times kx over m equals f minus kx. So we take, what we need is f. So f is equal to m kx over m plus kx. Or in other words, f is equal to kx, open bracket, m over m plus 1. And if you are if you like beautiful answers, and we all do, so kx m plus m over m. And this is the solution. This is the answer. Okay. Do you think, guys, on a scale of 1 to 10, that you understand problem 4 better now? And do you think that you'll be able to solve it if you haven't already? Can I get a vote? Understand it better. Okay. Better now. Yeah, just, I mean, the one very important thing is that they are accelerating, and the acceleration is the same. And once you realize that, it becomes easy. Well, you know what? Let's do another one, a similar one. So let's say you have problem 7. Let's say you have a trolley, another one, and so the friction force here. So there's a block, and there is a friction force. There's a friction force here. The maximum value of the friction force, so let's say mass is 2 kilograms, 2 kilograms, and you know what? I'm gonna do mass is 2 kilograms and mass is 10 kilograms, and there's a force F, and the coefficient of friction here, coefficient of friction is 0.7. 0.7. What is the maximum value of F, is the maximum value of F, so that the top block does not slide off. What is the maximum? What is the maximum value of F so the top block doesn't slide off? So once again, draw the forces acting on the bottom block and on the top, block and on the trolley. On the block, there's only one horizontal force, and that is the friction force. And the friction force pulls it forward, F friction. And for the trolley, there are two forces, two horizontal forces, and one force is to the right, F, and one force is to the left, which is the force of friction, which is the Newton's third law pair of that force. So F friction. So these two forces is Newton's third law, Newton 3 pair. Because if the bottom block pushes the top block forward, that means the top block pushes the bottom block backwards. If there's a friction force. So if one rubs against the other one rubs against the first one. And let's write down Newton's third law. So mass, so this is mass acceleration is equal to F friction. And we know that force of friction is less than or equal to mu r. So mg and r. So we can safely say that r is equal to mg. So this is equal to mu mg. So ma, in other words, is less than or equal to mu mg. Mg. So m cancels out. So acceleration is less than or equal to mu g. So the maximum acceleration the top block can experience, max. So if it's always less than or equal to, then it's equal to mu g. And we're going to stick with that because that's the maximum value for the acceleration, which is 0.7 times 10, assume g is 10, 0.7 times 10, which is 7 meters per second squared. So the maximum acceleration of the top block is 7 meters per second squared. If you attempt to accelerate faster than 7, then it will just slide off. Now for the top for the trolley, then we have force is mass times acceleration. Mass acceleration is equal to F minus force of friction. And we know that force of friction is maximum when it's almost sliding. So force of friction is mu mg. So ma max minus F minus force of friction, we know that it's equal to ma max. So the maximum force is equal to ma max plus ma max. A max. Or in other words, F is equal to m plus m a max, which makes perfect sense. The force is equal to mass times acceleration, and the combined mass of the two is m plus m. And that equals to maximum force is 2 plus 10, so 12 times 7, 84 newtons. That's the answer. Okay, any last minute questions before we finish? I hope that helped. This is right. So I decided to do some more questions on physics, just for you to get a better grip on those. Otherwise, okay, then everyone have a lovely Christmas, and I'll see you in a week's time. Okay. Welcome. See you.